thinking about the design and biases and things like that. With quantitative variables and some of the summaries, there is sometimes a judgment of opinion. It's how skewed is something, how close are numbers to what averages and medians, how close are they. So a relevant discussion is usually what's looked for there. For some of the technical questions, do you get the right numerical value? Often partial credit can be given, particularly on the exams. I look at how things were done. If you show work and are doing things essentially right and seem to be knowing what's going on, but the number's wrong for some reason, a calculator error or just a typo or something, then that's usually much less of a penalty than if you just write it. If there's a number there that's wrong, I have no idea how you got it or if you understand the question. But if there's a little more work shown, then I give you partial points for it. Yeah. So anyway, yep. I try to ask at the end of the class, to hand in homework just in case you haven't done it yet, so you don't walk out the door forgetting to turn it in. But today we're going to talk about some quantitative variables and summarizing those. Right? So we started out, we're going to do an experiment or a survey or get data somehow. Some of the variables will be categorical. We might describe them with tables, and percentages, and things like that. Others are going to be quantitative. They're going to measure weight or volume or chemical concentration or some other aspect of things and want to summarize them. So let's start out with a really simple example. Maybe this, I've done it in different orders at different times. And so let's say we have 5 values. No real context at this point. So n equals 5 is going to be our sample size. And they're going to be quantitative measurements of some site. So 12, 8, 5, and 25. So let's say that these are our 5 values right here. So they add up to the sum of these things. Should be 55, so 30, 40, 55, good. Often we'll refer to quantitative measurements in general, kind of in the abstract by symbols. So if the variable is recorded as x, we could call this x1 and x2 and x3 and x4, kind of those values. And so the sum of those values using these symbols would be x1 plus x2 plus x3 plus x4 plus x5 would mean add up to the 5 values that you have. Okay. In a little bit more compact notation that the book uses for summation, right? The big Greek letter sigma is the general math term for summation. And we're going to add up different objects, x of I. So I there functions as an index, right? And so the index in this case would go from 1 to 5. Taking x1 plus x2 plus x3 up to x5 and add them up, and we get a sum of 5. And so one measure that we use for quantitative data to measure the center of our values, or what's kind of the central location of our data measurement, right, is the sample average, or x bar. So this is either called the sample, let me write that here. Right, so measures the center. Right. X bar is either called the mean or average, right, of values, and it's the arithmetic mean. So you add up all the values. In general, we might have n as our sample size. I want that to go away. And add those all up, and then divide by the sample size. And that gives us the mean or average value. In this particular case, since n is 5 and our sum is 55, our average is just going to be 11. And so 11 is kind of in the middle of these values and would generally kind of describe where the center of these 5 values were. If you really had a data set that was only 5 values, I'd rather you just tell me those 5 values and not summarize them, because that's a small data. But if you had 100 values, then it's more useful to do that. So that's one measure of the center. What's a second common measure of the center that you've heard of or used before? Yes?
Median.
Yeah, median, right? So for these data sets, so the median, right? If you put the numbers in ascending order, it's just the middle value. Or if you have an even number, like if you had 100 values, it would be between the 50th and the 51st, right? Maybe the average or the central two. With some number in the middle that puts 50% below and 50% above. So in these cases, if you put them in order, 5, 5, 8, 12, and 55, the median is going to be 8. For these values. And again, it describes the center in some way, because half the values are at that value or below, and half are at that value or above. And they're slightly different, right? Now, when people talk about comparing these two things, they talk about, besides how to calculate them, is either of these values terribly sensitive to extremes within the data? Sometimes things that we measure, we will get a few really extreme values. If you sampled counties in the United States and you looked at how many cases of flu are in each county, many counties in the United States are 5, 10, 20,000 people, not so big. But there's a few counties around the big metro areas that are in the millions. Right? So if you count the number of flu cases by county, you're going to get a bunch of small numbers. And suddenly you're going to get something in the thousands, because you pick New York or Chicago, Cook County, that's Chicago, or another county around a large metro area. So those would be some extremes. So if you put the average number of flu cases per county, which measure, the mean or the median, is more influenced by the presence of an extreme value? Yes?
Mean?
Mean. Why is the mean more influenced?
Because we have an outlier, it kind of draws your values out and makes it a large number, and when you divide it by the number of values you have, it comes out to be
Pulls it up quite a bit, right? Yeah, so in the median, right, you could take this biggest value out here and make it 555, right? And still in order, 8 still here in the middle, right? So if we had, instead of our values being like they were, if we had the largest one being 55, if this was x1, x2, x3, x4, x5. So here's our one change instead of 25. Now the sum is 85. So now our x bar is the sum over our sample size is now 85 over 5, or 17. Before it was 11. But the median is still the same. Right, putting our values in order, we get 5, 5, 8, 12, and 55. So still 8 is in the middle, it's unchanged. So the mean is more sensitive to those extremes. Neither one's really superior in terms of describing the center. It kind of depends on how you want to think about those things. So we're going to look at some slides. Are they here? I've jumped ahead a little bit and gone through one example. This is incorporated here as an example. But I thought you'd better start with this and jump into a couple other things that we'll do shortly. So they behave a little bit differently, measure the center in a little bit different way. So let's think about a couple statements, right? So somebody could say that the mean income in the economy is rising. The mean per capita income is going up. So the economy is getting better. And then somebody could say, no, the median income actually is decreasing. So the economy is getting worse. Is it possible for both of these statements to be true at the same time? If it's possible, how could it be possible? The mean is going one direction, but the median is going in the other with one population. Yeah.
There could be maybe one or two extremely large numbers, that sort of skew the mean higher up, but then the median itself will still reflect a smaller number if there's more people on the smaller scale, maybe.
Yeah, right. So it depends, the mean is sensitive to those extremes. Right? So if the upper 1% is getting a lot more, right, then the average should be pulled up. But the median concerns where that 50% is. Right? So the 50% is shifting down a little bit. Or you could have it that the top end is going up far enough to compensate for a little shift down here. Right? So you could have both things happening at once. So it's political, right? It's interpretation. Which do you want to focus on? Which do you think is the more important one? The mean, if you multiply it by the sample size, gives you the total. If you're more focused on the total, you might be more concerned with that measure or the average. But the median says something about the middle. So if these things, yeah, so if there's extremes. But the other aspect of quantitative data that we'll usually do, besides describing just the center through these couple of measurements, is interpreting them, whether the mean and median and what they portray for a different data set, is really important to look at the data. Right? So look at the distribution. Look at the distribution of the different values that we have. So a primary tool for this is going to be a histogram. So a histogram is a graphical depiction of the data. We'll put our range of values on the x-axis, and then take a little bin, a little width, a little interval there, and either count the values that are in there or figure out what percent of the values that are in there relative to other areas, and make a little picture. And if the picture looks kind of like this, it's kind of decreasing as it goes away from the center. This type of illustration of values is mostly symmetric, right? Kind of equal spread on the left and the right, like that. And if it's kind of like this, more or less, the mean and the median are about the same values, right? In any one particular data set, it won't exactly match, but it's kind of close. And if you happen to have an extreme value that's sticking out there, you want to look for that. Something like that sticks outside of the pattern and looks particularly extreme is often referred to as an outlier. Just a value that's unusual in comparison to the other ones. And that outlier will pull the mean up a little bit, but it won't really affect the median. So if you saw a difference, it could be partly related to that, and slight differences in the shape. Another dominant shape we look for is a pattern of values that's skew. If the histogram of values, here's all the different values in some application, kind of followed a pattern that had a longer tail going out this way. This one I would call skew to the right. The tail and the extreme values are kind of stretching out there. The thing that's on the vertical, again, is either the number of observations or the percent of observations, if you normalize it to that. For this type of graph, which do you think is going to be larger, the mean or median? Yes, mean. So in these cases, the median is usually less than the mean. Because the mean gets pulled up by these large values. If a few of these were even bigger or more extreme out there, they would pull the mean up before. But the central 50% of the data is like half the area, right, which is mostly back here versus that. And it doesn't matter how far those stretch out. The median is a little bit less than the mean. You'll get skew. Data occurs in a lot of different cases. If you look at, if the units that we're looking at are counties in the United States, or maybe schools, there's often a bunch of small schools, medium-sized schools, and a few really big ones. A lot of measurements on size of populations is skewed to the right. Of course, it's possible to have skewed the other way. So you can have something that kind of bunches up over here, and then kind of trails off with things. With this shape, it's skewed to the left. I call it left, pointing out that the tail, that extreme, is going down there, and then the relationship is usually reversed. So the mean is usually less because these small values don't add much to the sum, but you're dividing by the sample size, so it's a small value, and it goes the other way. And that can happen for a number of observations. You know, if you're doing educational testing, hopefully a lot of the scores are clustered at a higher level. If there's a few scores that are lower, you can create a tail going out like that. When we look at surveys and what percent of the questions get answered by people, on a particular survey, a lot of people answer most of the questions, and there's a few people that drop off earlier and they get smaller numbers. So kind of the response rates by questions on large-scale surveys tend to look like that, right? And that's more skewed to the left. So we're interested in those patterns. So when you're going about describing some data, let's go back to the beginning of the slide. As we're focusing on describing data, the context in which this would really happen is we would be doing a study. We have a sample, or maybe even a population of humans, and we have some data on them. There's some categorical variables, there's some quantitative ones. The quantitative ones in real applications have units of measurements, whether it's dollars or weight or volume, or some scientific measurement of concentration, or force or energy, and it's important to keep track of those. If you're communicating with anybody about your data in a study, you want to use the right units and know what those mean. But in general, when you're encountering a data set or gathering data, it's one area where you can be creative. And the knowledge you have in a biological or other scientific problem or social problem comes into use because you have some idea of which variables are important and interesting and how they might relate. And the point of descriptive statistics is to look at that, to get summaries that you can communicate and start generating hypotheses and finding things out. Right? So we're going to look at quantitative variables and going over a number of different aspects of that. As one example of a larger study is some data that I have from a survey that was done in 1996, 1997. Right? So back in the 1980s, the U.S. government won court cases against the tobacco industry. And they found that the tobacco industry had been hiding the amount of the addictive nature of tobacco, and they started causing cancer and other health problems. They've been intentionally minimizing it, and they had documents that said, we realize this is bad, but we're going to promote it anyway. So they had to pay billions of dollars, like $200 billion to the states, to compensate them for health costs and other problems. Right? Some of that money went to education, some of it went to medical treatment, and part of it went to data collection, to monitoring smoking rates, educational campaigns, and making any difference. So one part of that was a survey. Different states had different organizations that did the survey. The Gallup organization did the survey in California. About a quarter of the population, adult population, was smoking at that time. So they interviewed about 6,000, 7,000 people, adults, mostly by telephone at that time. And 1,379 of them identified themselves as people who smoked sometimes or regularly, or every day. Right? So self-identified smokers. Right? And some of the things that they recorded, was gender, male or female, age in years, self-reported age, self-report number of kids living in the household, probably marital status, although I don't summarize it here. They had questions like salience, like how much of an issue is teenage smoking in your community? Is it very serious, somewhat serious, not serious? A whole series of kind of opinion, attitude questions like that. Since these were smokers, they asked how many days do you smoke per month in a 30-day month? How many cigarettes do you typically smoke per day? Right? Then they asked things like, would you like to quit? Have you tried to quit? Have you seen advertising campaigns about quitting programs? Have you tried quitting programs and things like that? Some variables were derived, like in the medical tobacco addiction literature. People who smoke less than 15 cigarettes are called light smokers. If you don't smoke or haven't been around much smoke, 15 sounds like a lot, but in smoking communities, among people who smoke regularly all the time, every day, 15 is called light as opposed to heavier, more than that, right? That's associated with feelings of addiction and physical craving, physical response. Another question related to that is, how soon in the morning how long do you go in the morning before you have your first cigarette? If somebody rolls out of bed and starts smoking, that's an indication that there are more feelings of addiction than if they wait until nighttime or something. So they'd ask a bunch of questions. Data are usually stored in a computer in a rectangular array. Right, so here's variable names across the top. And each row represents one person. So here's someone who's a male, age 43, 4 kids at home, who give a salient response that has the third level, whatever that corresponded to. Sometimes they don't answer questions. So in the R statistical program, NA means missing. Right? They either refused or so they didn't know, and the interviewer couldn't get them to commit to a number. Like to quit, I think 2 means no, right? But there's a code for that. Often data are stored as numbers, but there's a code book translating what that means into things. Right? But yeah, that's some of the data that might be. So this one has 1,379 rows altogether. And part of learning about a data set, you want to summarize some of the data values to begin with. Right? So if we look at a few things, a few of the categorical variables are there. This random survey got more females to respond than males. Response rates were higher among females. So that could be a little bit of a bias. They probably do a little bit of adjustment when they do reporting to equalize the effect of that. This graph kind of shows the larger percentage of females than males. Some of the summaries, like we've done with categorical data. Right? Would you like to quit? About 70% say yes. Have you tried to quit? About 50% say yes. About 54% of the individuals are classified as light smokers. There's a few missing values. Right? 75 did not answer, would you like to quit? Right? So 75, it's not trivial, but it's 75 out of 1,600. So it's, if it had been 700 didn't answer, you'd really have some problems thinking about that question. But it's not an absolute cutoff how much is bad. Any is bad, but the smaller percentage missing is. In some applications, like if you're trying to look at revenues of car makers or something, you don't get anything from Ford and GM and the big companies, even one missing point is kind of devastating. Right? But if it's a survey like this where everybody's kind of treated equally, then it's less. You might do a few things for some of these qualitative variables, like the salience one about the series of teen smoking. So usually when you communicate things, instead of putting numbers up here, because who's going to know what the numbers 1 through 6 mean? It's good to use the words, and it's clear to do. We have a few choices sometimes for graphs. Sometimes they're helpful. In this graph, or you can see which one of these is exactly the highest one. Can't exactly see what the level or number of responses are there. You can kind of infer. It's about 325 or 375 or something like that. From pie charts, I don't know if you can tell which category is the largest or how those three rank in comparison or what percent they actually do. I think it's pretty hard to look at a pie chart and get anything besides kind of a really kind of gross picture, about those things. If you were just going through your variables and taking arithmetic averages, would you want to take an arithmetic average of this one? Would you want to report an average such as, 3.2? A couple reasons, right? It's not a quantitative variable. It's going from 1 to 2 is not the same as going from 2 to 4. It's not on that interval scale. And 5 and 6 out there, or the numbers that are put in the computer for recording the information. But you certainly, there's no sense in which you would want to average those in and put them on some scale. But once you've done that, some of those, get some idea of these different categories, you could look at some of the quantitative information. So here's one table, some of the quantitative variables for this study. So you sometimes what you call a 5-number summary, or you can report a few different numbers for things. The minimum is the smallest value, so this is a survey of adults, so the ages start at 18. 0 kids, 0 days per month, 1 cigarette per day, on average. I mean, people say they're sometimes they smoke, they're classified in the smoking category. So some people say, normally I don't smoke, so, or I go for a long time, but every once in a while. So they ended up in this group. The median, we talked about that, the middle values, a median of 40 years, median of 30. So half the subjects said 30 days a month, 30-day month, right? So half the subjects, at least, are smoking every day. The third quartile is also 30, the maximum, well, let's see. Right, the first quartile is 25. So a quarter of the people are smoking 25 or less. My impression is that it's usually pretty high, but not every day for everybody. The mean is reported. I mean, these should be reported as decimals, right? So these are the number of kids in the household, so 0.84 kids on average in a household. Right? You can report that. You don't have to round that average. Right? So 0.84. It could be interpreted if you had 1,000 households. Right? Then there'd be 840 kids in those 1,000 households, so the average is 0.84. The quartiles here are the 25th percentile and the 75th percentile. The median here is at the 50th percentile, so 25% are less than that value. And so that also describes a little bit about the information, the distribution. It's good to list the number that are missing or some indication of the kind of the quality of the responses. Anything unusual about any of these summaries? Anything unusual about any of the numbers? Yes.
So in the kids category, it says maximum of 44. Does that mean like someone reported 44? Or?
Could be, yeah. So in the data set, there's a 44 in that variable. So they could have read the question, how many children are living in this household? And, that might be interpreted as 44, depending on the dorm or some type of home or something like that, right? There might also be an error. Right? These are entered by humans, right? And so if the key stuck or if they use the key twice, maybe it should have been 4. Sometimes you can go back, and if there were paper copies of the questionnaire, and you could find that one and say, oh, it should be 4. You could fix it. Right? But increasingly, things are done on the fly on the computer, so they're just typing it into the computer, and there's no other record. And so if there's a typing error, it's hard to go back and fix things. This applies to medical studies. Increasingly, medical records are typed in, so if you're reporting blood pressure or heart rate and there's a typo, right? There's not much of a way to go back. Before, it was recorded by pen and paper and then put into the computer. So it's a new challenge for data collection in scientific studies. In this data set, there's nothing else right around 44. So if there was a bunch of 44, 41, 42 up there, we would think, oh, these must be some type of dorms or something like that. But instead, there's like a 21 and a 22 and then a 12. 12 could be real, right? That's a big family. 21 could be a mistype of 12 or 2 keys stuck together or something like that. These things are real, right? This affects studies. You find out by looking at data. Right? If there's ongoing monitoring that says, if you had a computer program that says anytime you enter more than 10, the typist has to confirm the number, right? You would catch this. And so you'd have to have a type in 44, and then you'd have to answer, yes, that is a real value. Right? So you could design the computer to try and stop these things. But it's there. You have to decide about what to do with it. Is that going to affect the median or the mean? That's going to affect the mean, right? It's going to pull everything up. If you don't like that, you might take that one value out, recalculate the mean, it'd be a lower value. it's best to note in the summary that you're writing that one of these values seems to have been an error and you took it out. Right? Cigarettes, 70 per day. Could that be an error? Well, 7 and 0 is not so close together. It's not like, if it's at 78, maybe that would be one missing. Right? But 70 is 3.5 packs a day. Basically, that as soon as one's done, you start another one. Right? That's full-on chain smoking. Right? That would seem quite unusual, but you really want to kind of look at it in relationship to others. Right? Well, this is on a couple pages down. I like to look at the smallest and largest values typically for a variable to get an idea of ranges. A bunch of people said just 1 cigarette per day, so that was, a lot of people are very light smokers. They have one, right? But here's 70. There are a bunch of 60s. So 70 is the largest value. It's a little bit outstanding, but there are a lot of people who are saying 60s. So here's a histogram of the number of cigarettes. Right? So it is skewed to the right. There's these couple of big values. These seem kind of outlying, but maybe they're real. Right? If it said 700, that's not realistic. Right? That'd kill you. Out. You're dead, right? So maybe it'd be hard to justify taking out that 70 from any analysis. Any other interesting patterns with that data set? Is that one?
Most of the people who have taken the study are light smokers.
Yeah, most are light smokers. Like most are under 20, right? So if amount of smoking is associated with addiction, most of the people are not smoking more than 20, right? Yeah. So, yes.
To add on to the 70 cigarettes a day, like the largest 10 numbers, there's 9 that have 60 cigarettes a day, so like 70 doesn't seem too far off, but like in our minds it does.
Yeah. Right, if you're not around smoking, not around chain smokers, then yeah, that would seem off. The most, but it's plausible behavior. Right? You see a little clumping there, right? So cigarettes are sold in packs of 20. Right? A lot of people report 20, or 40, or multiples of 10. People tend to clump. Right? There might be something associated with the way they're distributed, or that people, if you're smoking all the time, you budget for this. Right, you buy in quantity or something, right? So you budget how much it is, and it's probably easier to budget in 10s and 20s. Probably if you ask people about eggs, they report multiples of 12 or 6 or something like that because they're sold in those packages. Anyway, there's clumping that would come up in this and other things. The mean number of cigarettes was 13.81, and the median is less. It's 10. Here's a few other histograms. This is an age distribution. Right? This is a distribution of age, where the vertical axis here is the frequency or the number. So I think these go in every 5 years increments. So it looks like there's about 200 people that are between 35 and 40, or between 45 and 40 and 45. I can't quite see which one that is. This is the same graph, but as a percentage basis, so the percent of the sample. So sometimes they're presented other ways. Sometimes you can take one variable and you report it another way. So instead of age so far, this is time until they reach 100. So it's essentially the flip of this. The 20-year-olds have to go 80 years to reach 100. And the one person who's 99, there's one 99-year-old respondent in there, only has to go 1 more year. So it's depending on if you do the subtraction. A number of medical studies will do things in survival, time until an event, time until completion. And so you could have look at things one way or the other and get that. So when you describe these, you can use ordinary language, you can use whatever is effective for communication. You can describe, most of the values are in this range, right? And give a description of the range. You say a small percentage are above 80. There's 199 sticking out there as an unusual. It's slightly skewed to the right. So if there's a description poem like this, and you pick up on a little different thing than I did, but it still seems relevant, it's kind of a judgment call. It's a slightly, don't think you could claim it's symmetric. Some people might say this is strongly skewed, but I wouldn't say it's strongly skewed. But for some of those interpretations and descriptions, there could be a little bit of difference of opinion about that, right? But any questions about it? Usually a graph along with descriptive numbers gives a better way to communicate about data and to learn things. Here's a different graph on page 9 of the handouts there. This little one's called a stem and leaf plot. And in this one, it's good for a smaller data set. So I've taken 100 smokers, kind of randomly sampled from there, and these are their ages. So I took 100 values and put them in order down here, 18, 18, 19, 20, and so on. I happened to get an 80-year-old and 99-year-old in the sample of my 100 out of the 1,300 some. Right? And what this graph does up here, this depiction, is it takes the number and transforms it. Right? It takes the 18 and turns it into 10 plus 8. So the thing on the left is the 10s, 20s, 30s, 40s, and so on. It always adapts to whatever problem you're dealing with in the data set. And so this 8 over here on this green, 10 plus 8 are 18, and there's another 18. 10 plus 9 is our 19. And then in this row, it's 20. 20 plus 0 is 20, and so on. And then the top value, 90 plus 9 is our 99. And it depicts the data, right? So if you turned it on its side, it would be like a histogram, right? So it would show kind of the numbers that are in the different ranges. But then there's something else that what can you get out of this that you can't get out of an ordinary histogram? Yeah.
Like precise numbers.
Yeah, you get the precise numbers, right? You could take this and recreate this ordered set, right? Because you can get 18, 18, 19, and so on. So you could find the exact median. From a histogram, you kind of have to eyeball. Well, it's kind of in this way, it's somewhere in the middle of a bar somewhere. But in this one, you could find the lowest 50 and then the next 50 and find out exactly where the median is. Or if you add them all up, you can get the mean. You can recover some things. So the point of having things like this is people that were looking at statistics in the 40s and 50s, trying to move beyond just reporting one number, just reporting the mean, or just reporting one graph. For different data sets, you might use different flexible things. It's better for communication, and there's just different tools for visualizing to try and come to some understanding of things. We've talked about this, what impacts mean and medians, right? And the mean and median can have different interpretations. This last slide in here is kind of related to this, but I might have done it with this mean and median one. But one project I was involved with was some data analysis about SNAP, which is a Supplemental Nutrition Assistance Program. It's formerly called food stamps. And the idea that individuals who have a low enough income and qualify can get some funds to use for food and a few other things. Right? And there's a federal government program administered by the states. And now it's on these electronic benefit cards. It's grown to over 30 million people a month in the U.S. And the program's about $90 billion a year now. It grew significantly during the last recession. Right? And for some people, it's a very significant portion of their diet, and particularly at the end of the month when paychecks start running out, things like that. And it was in the news today, or yesterday, right? That because of the partial government shutdown, they're sending some benefits to these electronic cards early, but it has to last people for the next month. And if the shutdown is not done by March, there's no more funding. And so the 30 million people wouldn't get that. But so if it's not, one consequence of this partial shutdown coming next month is a suspension of these benefits. But with this $90 billion program, there is something called trafficking. Right, in which somebody would take the benefit cards to a store that would, engage in this, and they would tell the owner, "I'll sell you $40, $100 of my benefits if you give me $40 in cash." Right, so the store would ring up $100 of goods, milk and diapers or something, bread, but not give them anything. Instead, give them the cash, but bill the government for the $100. So that happens. They catch stores doing this. They investigate this. It happens more in small convenience stores that are open 24 hours. and have one register versus multiple registers. And it doesn't happen, they don't think, in large grocery stores and places like Walmart. Walmart is controlling their people because they don't, it's $1 billion for them as a store, so they're not going to let it get taken away by people stealing from them. So it happens, and they find it, but the percentage of stores, over the last 10 years, the percentage of stores found guilty of trafficking has been decreasing. And as things have become electronic and more regulated and more investigated, it's happening less as a percentage. Right? As more of the big retailers have all started taking this, more of that money is going into them. But the total and average dollars being trafficked is increasing. So of those that are still doing it, they feel that it's increasing in numbers. So just like the mean and median go in different directions, percentages and averages can go in different directions. And so it's part of a, knowing more than one statistic or one sum rate on the same problem often is important for that. But in any case, any questions about what we've done so far? So a couple things to do, right? One is transformation. Right? Well, first we're going to do some measurements, as pointed out in the book, of concentrations. Concentrations of blood alcohol, concentrations of various vitamins, nutrients in the blood, concentrations of certain chemicals and these things are often measured on a scale that is inherently fairly extreme. So some forms of chemicals might be measured on the order of 10 to the negative 2, 10 to the negative 1, 10 to the 0, 10 to the first, 10 squared, 10 cubed, something like that. All right, so this is a number, 0.01, 0.1, 10 to the first, or 10 to the 0 is the integers, 10 to the first is the order of 10, 20, 30, hundreds, thousands. So if you're looking at, parts per billion or parts per million of some chemical, ozone at ground level, a lot of places might have really small measurements, but then other ones will be just way off the scale, several orders of magnitude bigger. And if you take a sample where you have a bunch of these measurements and then some things that are in thousands or hundreds of thousands, the average is dominated by those big ones. Right? At the same time, the median doesn't really respond to the fact that there's some of these extremes that are out there. So something that's in between that is called the geometric mean. So honestly, we're not going to do a lot with geometric mean as something that we'll calculate throughout the entire course. But in biology, ecology, measurement is something that you could encounter, so it's at least worthwhile to think about it for a little bit. So as I've written these things on kind of a multiples of 10, if you take the log base 10 of some value, if these are the values x, if you take the log base 10 of these things, what it returns is the power up here that leads to that conversion, right? So the log base 10 of 10 to the negative 2 is negative 2. For this one it's 1, and then 0, and then 1, 2, and 3. The log base 10 of 1,000, that's 10 to the cubed, is just 3, right? And so these log base 10 values, right, look a lot less skewed kind of than the original ones. So a transformation is when you take data and then change its scale and change it in some way, right? So if you take the average of these things on the log 10 base scale and then raise that back up to the 10th, that's called the geometric mean, at least to a base 10. And so this will be another measure of the center, but computed another way that's kind of responsive to the scale. And so this thing, this log base 10 of x, the average of those would be taking an average. The bar, the x bar over top means that. But now the thing that we're taking the average of is we're going to take the log base 10 of each value we get. and take the averages of those. So let's look at one numerical example to kind of show how this goes. Yes.
What's on top of the summation sign?
It's supposed to be a little n for all the observations. So here's my little numerical example, right? So here's the values of x originally. 0.01, 0.02, 0.02, 0.3, 5, 82, and 1006. There are 7 of those values. So take the average of those, add them all up. Right, it's dominated by the 1006. The average ends up being 156.2. The median, if you put these in order, 1, 2, 3, the fourth value here is 0.3. So the mean and median are totally different in terms of what they describe. To do the geometric mean, we take a log of each of these things. Some people take the geometric mean maybe to a log. Depends on how it's recorded, what the geometry is. If it's multiples of 2, like a doubling, you might take a log base 2, like an example in the book. Sometimes it does it with a natural log. But in any case, 10 is, that's how I made up this example. The log base 10 of these different things. This is negative 2. Negative 2 is negative 1.7. Negative another one of those. The 0.3 is negative 0.5. Log of 5 is 0.7. If I had a value of 10, that would be a value of 1 on this scale. This one's 1.9, and this is 3.0. So the average of these things, log base 10 of these x's, the average of those ends up being 0.04. And so then the geometric mean is 10 raised to that power, which is 0.9. So on your calculator, right, you can take 10 raised to a power. You can do exponents. And maybe in math, you primarily have done integer exponents, taking things to the square or the cube or maybe -1 to get 1 over something. But you can put decimals in there too. And so where does 0.9 fall in? It falls a little bit higher up here than the median. It is pulled up by these big values, but it doesn't have the extreme pull that the average has. So it's just another measure of the center. And so for some, if you're in a science, and you're going to take a lot of measurements that are on these multiple scales, the geometric scales, then this will be a common thing that you would see. It's just another comparison. It might be relevant to give the mean, the median, the geometric mean, and there's some other ones, right? Harmonic mean, and some other varieties of that. Okay. So we will do, so that the next homework that will be posted, probably on Thursday, we'll do a little bit of these summaries using the computer. Right? So we're going to use, some of it will be problems by hand, and some of it will be problems using this R statistical package. So I'll show you this second handout has there's a few commands on there. Right? So we're going to look at a few examples there. So when you start up R, there's this thing called RStudio. And we'll do more of this on Friday. To get R, in case you're, right, to get these programs, we'll go over it, we'll do an example on Friday, take a little bit more time. But if you look for a place called CRAN, just Google, Comprehensive R Archive, you can download R to your computer. And then there's a place called RStudio. And if you search for that, you can download this other program I run called RStudio. Download. And there's a few buttons to click there. They have a version for PCs or Macs, or if anybody's running Linux, there's versions for that. And you download R, and you download RStudio, and you get these two icons on your desktop. You click through it, it sets up, you can do all the standard things, choose all the free versions. RStudio has some big enterprise versions that companies might pay a lot for, but we can take the free one is perfectly fine. I've done that on here some time ago. Here's a little RStudio link. So I click on that, and this thing with either 3 or 4, sometimes it looks like this when it starts out, 3 or 4 different terminals shows up. Right? And what I typically do to do that is here is a file. You can toggle through these different things over here. But this one under Files shows you something about where RStudio is looking for your data. Right? Where is it going to store things? Where is it going to look for it? Right? In a lot of programs, you have to tell it where your files are located. So you can look through here. So here's my lectures. We're in lecture 5. And I can look through here and see, okay, here's some nutrition data, rock and roll data, lakes data. And then I can set this as a working directory. So it will tell what I see there, then it will tell RStudio to look there for my data files. Right? And I've run it twice now, and that's fine. Right? So what this lakes data set is, if it's open, right, is just an Excel file. It's saved as what's called a CSV file, which is kind of a little simpler form of Excel. You can type it into an ordinary Excel and then save it as this file. This is just a real convenient way of doing it. So this one, there's 53 different lakes in Florida. Name of the lakes, measurements of alkalinity, pH, calcium, chlorophyll, and some other things on mercury. That are in there. The number of samples that were taken at the lakes. Some lakes seem to have been sampled a lot more than others. But in any case, all those different measurements, right? One row for there, right? So that CSV file, you can do a bit of data summary in Excel, but it requires adding some formulas, and every place that you go with Excel might have slightly different versions and things in. But this still is a useful way to store your data. In R, we can start up here with something called a script file where we save commands. Right? You can type up here and save these things. So I'm just going to kind of cut and paste this in here. But I can type directly in that command window there, that little console. And what this command is going to do is read in that data set. It's going to read in a CSV data set. I'm telling it to keep the header because there's the variable names up there. Right? And I do that, and it loads it in. Right? So there's 53 observations of 12 variables. Here are the different ones. This environment up here tells me kind of what's in there. I can see my objects that are there. So that lakes variable, that name there, is all 53 observations and all 12 variables. And so my data are stored in there. I can look at the first 6 rows. It's called looking at this little command head. Looks at those rows. Here's the rows for the lakes, the alkalinity, and so on. I can look at the tail is the last ones. Right? So they're in alphabetical order, and so you get these last ones. My experience is that when reading data in from projects, it's always good to look at the top and the bottom. Because at the bottom, there's sometimes blank extra rows, or people have put in totals or summaries, and you wouldn't want to average those into everything if it's already been done. At the top, people sometimes put extra comments in rows, and then that kind of messes up. Sometimes I take a data set and then make a copy of it and cut out the top stuff and the bottom stuff, so I just get my data and read it in. But that's right. So you get some type of clean thing in there. Right? And then all these variable names are associated with that data set. So it has the lake name, the alkalinity, pH, and so on. We can look at the values that are there by putting a little $sign and then picking the value we want. So RStudio See, I push the dollar sign and then it's popping up my choices. It kind of helps you. So it's kind of a nice interface like that. Well, I want to look at all my pH values here. Here's all my 53 pH values. They're in a list. Right? To avoid typing that little dollar sign business, I can attach, it's called attaching, attach that lakes. I think I'd already done it, so never mind about that once before. So, but it's attached, so now if I type a variable name like pH, it knows to look in the lakes data set and use that one. Just a little convenient thing that we'll do it 15 times during the course of this class, and so it's just something that a way of working. So if I go down here and now type pH, where did you, right, that one. It's case sensitive, as you can see. And so now I have my values there. For those, then I can do commands on those. I can make a histogram of the pH values. So this is a histogram of those 53 lake values, pHs. Anything interesting about that? Yes?
It's pretty symmetric.
That's pretty symmetric. Yeah, I wouldn't, think it'd be symmetric, but but it is, right? Would you want to swim in all those lakes? No, some of these are pretty bad, right? pH of 7 is basically neutral water, right? And so some are very acidic and some are more alkaline. So really surprising stuff going on. If we summarize pH, see, once the commands are up here, I just type run, it'll run what's in that line and save me the typing. Right? So this is the minimum pH is 3.6, the maximum is 9.1, the mean is 6.59. If I just wanted the mean, I can do just the mean of pH. Oops. It has a little toggle, so I can do my arrow keys to go back and forth through my command. So where I made that mistake, I can just erase it and type it again. And I got pH, and it reports a few more significant digits. For this, on your homework, if you wrote 6.59, that'd be enough significant digits. Right? You don't need to write all 6 or 8 of them. But if there's, 53 observations, 5.6, 5.59, 6.591, you might do one more. But you don't need to do a crazy number. Right? Median is another command that it has. That comes out of there. Here's the alkalinity graph. I don't know the units of measurement on this one exactly, but how does this one differ? It's pretty skewed to the right, yeah. There's a lot of them that are below 40, and then there's some that are really, really extreme, right? So if you do summarize of alkalinity, right, you get the mean of 37, but the median is only 19. That skewness affects that. Right. So when you are going to be given a homework assignment to do something in R, it's going to be kind of like this. Right? A data set that you either read in, or if actually I give you an R data set, right? There's an R data set format. You can just open that R data set directly in RStudio and it will pop up with the variables. Right? So you can download it from the website to some file, location, go to that location, open RStudio, open it in RStudio after you install it on your computer, and it goes really fast. This other data set's on there. You can look at those different commands. There's this other data set called Rock and Roll. We'll look at one more just for fun. Quick example of some of the things that you can do. Right, so this particular data set, these are individuals who were inducted into the Rock and Roll Hall of Fame. Individuals or groups, right? Whether they had female members in the group. It looks like just from the start that there's an imbalance there over time. People were inducted in different categories. The number of people that all were inducted as a group, like the Beatles, all 4 of them together went in. Right? And this is just a subset of the data, all through this. So kind of interesting. If you read that into R, if I go to the right place, I gave it a short name, R&R, just so I don't have to type any big thing. Right? The first observations of that one are here, ABBA, AC/DC, and so on. Right? So the categorical variables, we can do things like tabulate them. Some people are in there as early influence, or performers. Or, non-performers could be agents, or people that have done technical developments and things like that. The people variable is actually the quantitative variable, the number of people. But in this case, it's almost just as well to put it in a table, because it's not all that many values. You could do a histogram of that. And that little Darlow sign on there, I haven't attached it, so, but I can still refer to those. Is anybody interested in the largest group? Any guesses about what groups might be large? Historically, that might have been conducted. Has anybody been to the Rock and Roll Hall? It's in Cleveland. It's kind of fun to go sometime. So the sixth, Parliament Funkadelic. I have 16 members consistently over their time. For those that are bigger than, so in R you can pull out different pieces by little logical constructs, and we won't do a lot of that right away, but you can get subgroups and things. So greater than 7 people, here is some. Early influence when I don't know that person, but I've heard of those other groups. I'm kind of interested in Frank Zappa, so Frank Zappa was inducted by himself as a musician and composer. He, though, also typically had bands that were very large. Multiple percussion, horns, and multiple guitars, and other people doing strange things. And so there were usually a dozen people on stage, but he was the only kind of sole person directing it, and it kept changing over time. So it's although I think of it as very large musical performance, when they inducted it, it was just one. So you kind of have to figure out what variables mean and how they're recorded and why, and by a little bit of exploration you can learn something. On Friday we'll do more with describing spread and do a little more practice with the computer.
So do you want me to hand in the homework just as soon as I go?
Yeah, if you could get it by Friday.
By Friday? Yeah.
Yeah, so
Professor, do you know who's in the most time?
I don't know who's in the most time. Eric Clapton is for the Yardbirds and
The Yardbirds,
Cream and
Cream.
Cream solo, yeah.
I forgot mine. I'm going to go do it now. Are you going to be able to get it, or do you want me to?
I'll probably be back in my office, John Marie 259.
259?
Yeah. If you go down the stairs, kind of back in there, but yeah. Yes. I don't have, I guess. Can you turn it in by Friday?
Yeah, he's fairly on.
Okay. That'd be fine for a time.
Have a good day.
You too.
Keep going, Professor. See you Friday.
See you Friday then. Great, thank you. I tried to fold it. I'll try to fold it a little bit. I'll probably save it when I get back. Thanks.
So you want us to download the program by Friday and work on some of the stuff?
You don't necessarily have to work on anything. You're welcome to try it. I'll probably illustrate it here in class. I mean, if you want to bring your computer and do it in class, you can do that. But in my experience, it takes 5 to 10 minutes, maybe.
Okay.
Maybe not more than that to do it. But we'll kind of illustrate it, and then I'll get a homework posted. Some of the homework will be book problems where you won't need it at all.
Yeah.
But we'll, make a couple of graphs, do a couple of summaries, and then write something about it. So it's kind of a gradual introduction to just
Okay.
get a few things going.
I thought you wanted us to do all of it tonight, and I was just
Oh,
like,
no,
oh,
no.
I might need
No,
your
this
help.
is one illustration. Friday and Monday we'll do illustrations too, and then a homework due on Wednesday. So
Okay, thank you.
multiple times, see it, not all at once. Somebody leaves